Way back in 1977, we got a 72-second message from deep space, and then nothing. Absolute silence. It's one of the biggest mysteries in astronomy. But what if the solution isn't about waiting for a new message, but about finding one we might have already recorded?
So, let's just dive right into this pretty wild idea. We're not just talking about waiting for aliens to call us back. This is more like a cosmic cold case, where the most important piece of evidence could already be sitting in a digital trash bin somewhere.
All right, so for a quick refresher, in 1977, a radio telescope picked up this incredibly strong, really unusual signal. It lasted for exactly 72 seconds, and poof, it was gone, vanished, and we've never heard it again.
Now, this signal was so perfect, so unlike the usual background noise from space, that the astronomer who found it, a guy named Jerry Amon, he just circled the data on the printout and wrote, "Wow," right there in the margin. I mean, what else could you say? The name stuck, and so did the mystery. But see, this wasn't just some random blip of static. The signal had a definite shape to it. It rose in intensity, hit a peak, and then faded out smoothly. And that distinctive shape is absolutely key. It's like a fingerprint. It proves the signal came from a fixed point out there in space, and our telescope just happened to sweep right past it. It was a perfect alignment, not just some lucky accident.
And this is where the detective work really starts to get interesting. That original signal wasn't random at all. It left behind a very distinct fingerprint. And what that means is, if it ever came back, it would have to leave the exact same print. It would have to follow the rules.
And here are those rules. Any real returning signal has to come from the same little patch of the sky. It has to be on the same radio frequency, that same station. It needs to have that exact same 72-second rise and fall shape. And it has to be a super concentrated, narrow signal. You know, these aren't just clues. This is a strict checklist. If a candidate signal doesn't tick every single one of these boxes, it's just not the one.
Okay, so if we have the rules of the game, can we figure out the perfect moment we might have caught it again? Well, that's exactly what some new analysis has done, and it focuses on 3 key factors. So the formula for catching it again is pretty simple when you break it down. First, you need alignment. The telescope has to be aimed at the right spot. Second, you need observation. It has to actually be turned on and listening. And third, and this is the real game changer, retention. We have to be sure our own automated filters didn't just mistake the signal for junk and throw it out.
And this creates a kind of modern paradox, right? Our telescopes are way better than they were in the 70s, so our chances of observing the signal are sky high. But at the same time, we use these really aggressive automatic filters to clean up our data, which means our chance of keeping a strange one-off signal like the wow signal is actually pretty low. We might have gotten too good at cleaning things up.
So let's take that first factor, alignment. Because of Earth's orbit around the sun, the part of the sky where the signal came from, the constellation Sagittarius, isn't always in a good position for us to see. It's much easier to get a clear view at specific times of the year.
And what we see is that the visibility gets better and better through the summer, and then it hits its absolute peak in late autumn. For anybody in the Northern Hemisphere, October and November are the absolute prime months to be listening to that specific patch of sky.
Okay, now for that second factor, observation. We know the best time of year, but what about the best year to be looking? Well, the analysis went through telescope logs and found that 2025 was basically a perfect storm, a time when several powerful surveys were all scanning that exact part of the sky during that peak autumn window.
We can actually get even more specific. Within November of that year, the analysis pinpoints a few high-probability windows. But look, one of them stands out way above the rest, November 7th to the 9th. That's when the alignment and the telescope observation coverage were at their absolute maximum overlap. And there it is, we now have a specific time and a specific date to investigate. The whole question changes from, did the signal ever come back, to, did it come back between November 7th and 9th, 2025, and did we just miss it?
And right here is where the detective story takes a huge, unexpected turn. If the signal was detected then, where is it? Well, this new research suggests it's not anywhere that people have been looking.
This gets us right to the heart of that third factor, retention. The research argues that the evidence isn't in our nice, clean, final archives. No, the most likely candidate, and I'm quoting here, is not in the cleaned dataset, but in the data that was removed or downgraded. We have to go look in the digital trash.
What this means is the signal could just be hiding in plain sight. It could be sitting in a file of data that an algorithm automatically flagged as interference from a satellite or maybe even a cell phone. It could be in temporary computer files that were never meant to be saved. We might already have the evidence, but we just accidentally labeled it as noise.
This completely changes how we hunt for the wow signal. The mystery isn't about sitting around anymore and just hoping to get lucky a second time.
Yeah, the old way was all about passive waiting. The new way? It's active investigation. It's about using these rules to pinpoint a precise moment in the past, and then becoming digital archaeologists, digging through the data from that exact window of time.
So this leaves us with a really provocative final thought. This entire cosmic cold case has been totally transformed. The mystery might not be out there among the stars anymore. It might be right here, in our own computer archives, just waiting for someone to find it.
This whole explainer was based on the fascinating constraint-based analysis proposed by the researcher, inventor, and author Kevin L. Brown.